Hello students, welcome back to Vast Diversity. Today we're going to be studying the conic sections. So, conic sections, we were discovered during the classical Greek period, and the early Greek studies were largely concerned with the geometric properties of conics. And it was not until the early 17th century that the broad applicability of the conics became apparent and played a very important role in early development of calculus. All right, so we're going to be starting with conic sections. We already know one of the conic sections, and one of them is actually a circle, right? We know a circle. So let's take a look. Here are some of the conic sections. So I have two cones right here, right? Touching each other here with the vertex, and we have a circle if we intersect at any of the points, either top or bottom of the cone. Then if we slightly tilt the plane that we are having a cross section on, we will have an ellipse. All right, we're going to be studying what ellipse is. And then of course, if we do it perpendicular, right, perpendicular to the cone, we will have essentially an absolute value. But here, if we tilt it, we're going to get a parabola. And then if we do it the entire plane from top and bottom of the cones, we're going to get a hyperbola. So today we're going to be learning the ellipse, parabola, hyperbola. The point, we all know what the point is, right? There is a point on the plane. There is a line, right? We have a line all around the cones. And then here we have the two intersecting lines, which are laying right in the middle of the cones, right? Right in the middle at the center, right here, as at this point. All right, so, and of course, one of the ways we can represent those equations is through a quadratic equation, right? But let's take a look at the more general form of the second degree equation. I'm going to call it second degree, just so we don't confuse it with the quadratic equation. Okay, so let's say that, so we have ax squared plus bxy plus y squared plus x plus ey plus f is equal to 0. Right, so here a, b, c, d, e, f are real numbers. Okay, so we will be studying the conics specifically, which have locus, which is a collection of points, which would satisfy certain geometric properties. Right, so we're going to be studying essentially families of conics. So we know the very first one, which is a circle. Let's recall it. We did it in the previous lessons. So number one, circle. Right, so equation of a circle is as following. It's x minus h squared plus y minus a squared is equal to r squared. Okay, so we know that the center of a circle is at the point h comma k, and the radius is just r. Not r squared, it's just the r. Okay, so we know that, right? So let's go ahead and move on directly to the ellipse, right? So what is the difference between a circle and an ellipse? And here is going to be the main difference. So let's keep in mind that another way we can represent the formula for the circle is, so circle with the radius 1. Let's call it that way. So circle with a unit radius. So we call it a unit circle. So a unit circle has an equation x squared plus y squared is equal to 1. Right? So it's going to be centered at origin with a radius 1. With a radius just 1. So, however, there is there is a scale factor, essentially. We're thinking of it as scale factor as 1 for x and 1 for y. For ellipse, that would be slightly different. For ellipse, it would actually have some sort of factors. So let's go ahead and take a look at ellipse. How would we represent an elliptical equation? So the standard form of an ellipse centered at the origin with the major and minor axis. So in a circle, there is no major and minor axis because there is no scaling factors for the circle, right? So major and minor axis of length 2a and 2b respectively, where a is greater than b. So major axis is horizontal because a is greater than b. Major axis is vertical because a is greater than b. Okay, so what we can have, so the major axis is going to be as following. So we can have, this is going to be an ellipse, right? So which one is going to be the major axis? It's going to be the bigger one, right? So in this case, x-axis. X is going to be the major, right? Meanwhile, if we did similar thing but for y, right, let's go ahead and take a look at the example here. Let's do it green. So we can do similarly, but for the y. So which of the following axis is going to be the major axis? It's going to be the y-axis. And obviously, in the first case, we had x major, y is going to be the minor. And in the second case, we have y major, x is going to be a minor. So the vertices and foci, which we're going to learn right now, lie on the major axis, A and C units, respectively, from the center. So, and that's going to be the relation of C related to the coefficients A and B, right? So now let's go ahead and define what an ellipse is. So an ellipse is a set of all points x and y in the plane. The sum of those distances from the two distinct points called foci, and it's constant. So let's take a look at a provided figure from the book. So there's going to be a very good explanation and a visual representation of an ellipse. So as we can see, so any point on the ellipse is represented as x comma y. It has the major axis right from the center, so the biggest one, which is going to be the major axis, and there's going to be the vertices here and vertices here. So d1 plus d2, so that any distance from the point to the major axis, right, which is a focus point here. So the distance between any point to the focus point, the sum of them is going to be constant. The center of an ellipse and the minor axis, which is in this case represented as a y-axis. Okay, so let's demonstrate it with the previous two examples I showed. So we can also say that, okay, how would the axis differ and how would the equation differ? We'll give it a perfect example here. So we're assuming that we are centered at 0, 0, right, at the center of axis. And we're looking for the major axis, which is horizontal in this case. And major axis is going to be the y. So this is x here. This is case 1, case 2, as we talked previously. So we also know that we have the focus points, right? And focus points are located on the major axis, right? So you can see that for first case, we have it on the x-axis. Second case, we have it on the y-axis. Okay, perfect. So we also know that the sum of distances from the point to a foci, right, is going to be equal to the c squared a squared minus b squared, right? And essentially, we can take this as an example, right? So for case number 1, we will have that the distance, right, the distance between OB to the foci, right, it's going to be 2. So it's going to be square root of b squared plus c squared, right, from this side. And this is going to be d1, it's going to be d2. So we're going to have the same thing, right? So it's going to be 2 times square root of b squared plus c squared. Okay, and that's equal to the sum, right? To the sum of distances from the vertices to the foci. So it's going to be, in this case, it's going to be a plus c plus a minus c. Okay, So if we simplify this, we're going to get that 2 square root of b squared plus c squared is equal to 2a. So 2 and 2 cancel out, so we have square root of b squared plus c squared is equal to a. So c squared is equal to a squared minus b squared. And keep in mind that a here is greater than, right? Because a is on the major axis, always. Okay, perfect. So now, let's take a look at one of the important properties of ellipse, right? What's the difference between a circle and an ellipse? Is essentially that stretchness, quote unquote, right? Also, we call it ovalness of the ellipse. So, and in mathematical terms, we call it eccentricity. Okay? So, eccentricity, E, of an ellipse is the ratio of the value C over A. Right? So every ellipse, right? Every ellipse must have some sort of eccentricity, and that value will be between 0 and 1. Right? Because if it's 1, that means if it's 0, is nearly circular. For the perfect circle, it is 0. Right? For the very elongated ellipse, it's going to be very close to 1. Okay, so for the circle, it's essentially 0. So why is it important? Because we can use that in astronomy to study the orbits, right? And some of the interesting facts and interesting values of the eccentricity of orbits of planets. So some of the applications of ellipses, which is commonly used in aerospace engineering and astronomy. So here are the values for planets and orbit eccentricity. So that's how we know how different orbits are affecting the ellipse here. So we can see that probably the most circular orbit that we got is the Venus. Venus barely has any eccentricity compared to the other one, right? Mercury has the biggest one for the reasons of being very close to the sun, so it's more stretched of an ellipse compared to any other planet. Right, perfect. Now let's go ahead and move on to hyperbolas. So actually, let's go ahead and do parabolas first and then move on to. So the second one, parabolas, which we already know. We have done a lot of parabolas and a lot of second order equations in general. So we already have some awareness of what a parabola is. But let's go ahead and redefine it purposely for the conic section. So of course, a parabola is a set of points x and y in the plane that are equidistant. What does equidistant mean? It means equal distance, right? It has the same distance from a fixed line. So in this case, right, it's essentially mirrored. So, which we called a directress. And a fixed point, the focus, not on the line. So we can see this figure right here. And the vertex is the midpoint, right? We were talking in previous lesson about the vertex. Vertex is a very special point for a parabola because it gives us absolute maximum or minimum depending on the parabola's sign. Okay, so some of the standard forms of parabolas, right? We know the standard equation, but the general form of the parabola at the x-axis or at the zero-axis in general is as following. So the standard form of the equation of a parabola, visit vertex 0, 0, and the directress of y equal to negative p is as follows. So we can have a vertical axis, we can have a horizontal axis. Okay, and then if we would say on a picture, what's the difference and how would it look like in a vertical and horizontal axis? It would be the perfect picture for it. So here we have the first picture. The first case represents the vertical axis, right, which is our regular parabola. And the second one represents the horizontal axis, right, which is in this case y squared is equal to 4px. All right, so here we not going to do much problems on the parabola because we've done that in previous lessons. Now let's go ahead and move on to a new type of equation, which is called hyperbola. Hyperbola number 4 is going to be hyperbola. Okay, so hyperbola, let's go ahead and give a definition of a hyperbola. And of course, we'll take a look at a figure for the hyperbola. So a hyperbola is a set of points x and y in a plane for which the absolute value of the difference of the distances from two distinct fixed points, called foci, is a constant. Okay, and well, doesn't tell us too much, but let's take a look at a picture first. That's going to be much easier for us to visualize. Okay, so here is an example of a hyperbola. So here we can notice that, okay, so here we have an axis, right? Let's say it can be separated by axis, and here looks very similar to a parabola, right? A double parabola, one is on top, the other one is on the bottom, but it's close, but it's not the same as a parabola or as an ellipse. And the reason why is because of the equation that defines the hyperbola here. So a hyperbola equation itself looks very similar to what ellipse is, but the difference is we have a negative sign, right? Negative sign is a crucial difference here. So the standard form of the hyperbola, so for the transverse axis is horizontal, right? Which we have here in the picture, right? The transverse axis is horizontal. And here the transverse axis is vertical. So it depending on the parabola, the way it can face. So here is we having the vertical axis case in both, for both of this. Right, the horizontal would be a 90-degree flip. So let's take a look at the picture that literally shows the difference. So we can have it as this. Okay, and now similarly to what we had for ellipse, right, when we had to subtract the two, now the a, b, and c constants related by c squared is equal to a squared plus b squared, right? So essentially it is very similar to the Pythagorean theory. Okay, so here we can see clearly this is a transversal axis is horizontal, right? Because that's what connects the two foci here. So it's through the horizontal line. And here is a vertical because it connects it through a vertical line. Okay. And so when we want to find the foci of the hyperbola, we're going to be using the equations where it is equal to a squared plus b squared. Right, and it's very important not to mistake it for the ellipse because the equations can be very similar. The only difference going to be is in the negative sign. And of course, as you can probably notice, hyperbolas do have asymptotes, right? And those asymptotes are the oblique asymptotes, not the regular asymptotes that we have. Of course, there is an asymptote of the y-axis and the x-axis, right? Because we're never going to touch the y and x, but we can essentially, we are having the oblique ones. So for oblique ones, how do we find oblique ones? An oblique asymptotes, as we did in the previous lessons, can have the regular asymptotes of b over a for the transverse axis and a over b for the transverse axis be horizontal or vertical. Okay, and that's for specifically hyperbolas, right, that are centered at 0, 0, right? Because if it wasn't, we would have to shift the x values by the amount we have to shift the hyperbola. All right, so here would be a useful formulas to remember. So the hyperbolus asymptotes, the oblique asymptotes, with a center of 0, 0, are for the transverse axis to be horizontal. It's two equations, right? Positive b over a times x and negative b over a times x. For the transverse axis being vertical, we're going to have a over b times x and y equal to negative a over b times x. All right, so for the rest of conics, we've done points. We know how to do lines. And essentially, we also knew how to do parabolas, but we just decided to review some stuff on the parabolas. And of course, the two intersecting lines is going to be our soon upcoming topic on the linear equations and system of linear equations, specifically, which is represented by the very last conics, is the conics of the equations. All right, perfect. So that would be it for conics. And next lesson, we are going to cover the exponential functions, logarithmic functions, and properties of exponential. Great, thank you, students, and see you next time.